get started. I hope this record attendance is due to voting or something. So Sarah and I are going to split today's flipped lecture. Make sure you get all your questions in and you understand this completely. This is the perfect venue to make sure you understand things. The plan was for us to, we've got 4 lectures we're reviewing, but we're really going to focus on this question of how all the pieces fit together and kind of the end-to-end operation. And we're going to do that through a mix of review, examples, and actually hands-on illustration showing you how you can do this in practice. I suspect we'll get mostly through the end-to-end operation. If we have time, we'll actually do HTTP and DNS in more detail. So with that, for today, we're going to start by looking at this question of how L2 and L3 work together to achieve end-to-end communication. And we've kind of talked about each independently. This very last lecture, which I hope you watched, Murphy's lecture was actually about how the two work together. And we're going to focus on that because we found that that tends to be where people get the most confused. And so simplified view of the internet for today is that we have L3 that serves to interconnect a bunch of L2 or Ethernet networks. So we're going to assume all L2 networks are Ethernet for today's lecture. Reason this gets confusing is L2 and L3 have separate addressing structures, separate ways of doing forwarding and routing, and yet they work together. Every packet is carrying an L2 and an L3 header as it makes its way at every step in the network. And both addresses and both styles of forwarding come into play. And so knowing exactly when one kicks in versus the other and what role each one is playing is, at least I've found that's where people tend to get confused. So let's start with addressing. So we have, as I said, separate addressing at the L2 or Ethernet MAC addresses and IP addresses, which for today we're going to say IPv4 addresses at L3. They are different in that, when you think about where they come from, MAC addresses are kind of hard-coded in your device adapter, your network interface hardware that you plug into your machine. Whereas IP addresses, we've said it depends on where you are in the network topology. So they're actually assigned by operators. It's either manually configured or, as we've learned, they're assigned dynamically through DHCP. In MAC addresses, we tend to think of them as flat addresses, so they're not aggregation friendly. Whereas IP addresses, everything we've studied, they have this hierarchical structure, they're hierarchically allocated, and you allocate them in this way so you can aggregate or combine a whole range of IP addresses into one single prefix. Again, MAC addresses are portable. When you take your laptop and go to a different place, you take your MAC address with you. That's not the same for your IP address. If you move from Berkeley to someplace in San Francisco and plug into a different network there, you're going to get a different IP address. And finally, the role they play is again very different. Your L2 address is used to get you between two hosts that are on the same Ethernet or local network. Whereas IP addresses, this is the internet's end-to-end addressing scheme. This is what gets you across the internet. And so they have very different properties, as you can tell. These properties are not, I would say, independent. They are interrelated. So the fact, for example, that your MAC address is hard-coded in your hardware implies that when you move your machine, your MAC address goes with you. Right? The fact that your address goes with you means you can't aggregate them because you could have any addresses on your network. So you can't rely on a clean allocation that you can combine into one prefix. And the inverse is true when you look at the properties for IP addresses. The fact that we want them to be aggregated implies that you have to assign them based on where you are in the network, which means you have to assign them dynamically, given that hosts can come and go. Okay? Any questions on addressing so far? Nope. Okay, I have a few. Why do we need both L3 and L2 addresses? Any thoughts? Yep. Right. So there are two kind of sides to this story, right? And let's look at it both ways. First is why not use MAC addresses as a global identifier? And that's exactly the reason that was stated. You can't aggregate them, so it's not going to scale. We have 1 billion plus entities on the internet. You would have to have one entry in your forwarding table for each one. So MAC addresses are a non-starter because it just doesn't scale. Why not use IP addresses at L2? And there I think you're getting at an answer. But more crisply, do we think it's fundamentally impossible? to have IP addresses at L2. Yep. It's definitely the part about it's sufficient to use an L2 address is true. I would say it's stronger than that, that it's convenient to use an L2 address. And so the core of why we have or why we like L2 is it solves this bootstrapping problem. We've said L3, your address depends on where you are in the network, which means you have to be assigned an address. Right? And if you remember even the early steps of how end-to-end operation works, you have to get to your first hop router. So there's an initial bootstrap phase by which a host discovers its IP address, discovers how to get to its first hop router. And you could imagine, we use L2 as a very convenient way to do this because it has that broadcast discovery mechanism. You can reach your first hop IP router once you know its MAC address. So it's a very convenient way of bootstrapping. If you ask me whether I think it's fundamental, I would say probably not, but you would have to extend IP in order to do the functions that L2 is currently doing. It would need a flooding mechanism. You wouldn't need to be careful about bootstrapping routing within your domain before you can get out of it, and so on. And so by the time you're done doing that, I think IP would have had a lot of the functionality that Ethernet had. So the fact that Ethernet and L2 does that for you is just this convenient way of bootstrapping L3. Some of it is also, I would say, historical, the fact that by the time people started stitching together networks, we already had a number of Ethernet networks. So it made complete sense historically to reuse it. So, recap the answer, why do we need both? They kind of do different tasks for us under different constraints. We need L3 to scale. We need this hierarchical assignment of addresses, which is what rules out MAC addresses. But on the other hand, we like the fact that L2 networks have this plug-and-play or configuration-free operation. And so that's very useful for bootstrapping L3. Does that make sense? Yeah. Okay. So bootstrapping and discovery generally, what is the problem here is that a host, if you think about it when you bring it up, the only thing it knows is its MAC address, its L2 address. That's all it comes with. And so everything else you have to discover before you can communicate with a remote host. And that is the role of ARP and DHCP. So very quick recap of ARP and DHCP. They're discovery protocols. ARP is address resolution and DHCP is dynamic host configuration protocol. They both operate, important to remember, within the host's local or L2 network. And they both rely heavily on the fact that we have this broadcast capability, which when you think about it, that's a very sensible primitive by which to bootstrap something. If you don't know addresses, if you don't know where things are, broadcasting is convenient. But again, it doesn't scale, so doing it within a local network makes sense. ARP, very simple in operation. The initiating host broadcasts a packet saying who has this IP address, and everyone hears it. The host that has, or the entity that has that address, responds with its MAC address. So the request is broadcast, the response is kind of unicast, but at the Ethernet layer. Okay. DHCP is how a host kind of learns, or when it comes up, discovers its context in the I3 world. So this means its IP address, its net mask, the IP address of its first hop router, and typically the IP address of its DNS resolver. So quick review of how DHCP works. It's a pretty simple protocol. The client starts by sending a discover message saying, I need to be configured. Usually you have multiple DHCP servers on the same local network, but for now, let's say one of them responds saying, here is my offer. So this is a potential IP address, your net mask, and so on, all the parameters we talked about. The client then picks one, responds with a broadcast saying, I'm going to request this particular offer, and the server responds again saying, I acknowledge you now have this IP address. By the time we're done with all four messages, that is the point at which the client has its IP address. Until that point, it can't claim to own that IP address. Okay. We said, if you listened carefully to Murphy, that DHCP uses UDP. It's built on top of IP. Right. So this should give you some pause because it doesn't know the IP address of the DHCP server. It doesn't know the MAC address either. Right. It doesn't know its own IP address yet. And so how does this actually work? Okay. The answer is broadcast. All of these four messages are broadcast. And they're broadcast at both the IP layer, in the sense that your you use a special broadcast IP address, which in turn translates to a broadcast Ethernet address. Okay, so we're not actually broadcasting at the IP layer. That isn't a capability of IP. The only reason we have that broadcast IP address is it tells our stack to put in a broadcast Ethernet address. And then you're actually broadcasting at the Ethernet network. Yeah. Yeah. So why did DHCP build on top of IP? Why did it not build directly on top of? Why is it not an Ethernet level protocol? It's a great question. It's actually for historical reasons. It's a protocol that's used to bootstrap IP, and so the designers wanted it to be only IP dependent, not dependent on a particular L2 technology. So if we'd built it on top of Ethernet, we would have had to build a DHCP on top of every possible L2 technology. And certainly at the time, Ethernet was one, but certainly not the obvious winner as an L2 technology. And so this way, you have a general protocol that mostly only speaks IP, and then you just have this last translation from an IP to a local broadcast address. Make sense? So key ideas in both ARP and DHCP, we use broadcasting heavily, right? And that's fine. Broadcasting in general doesn't scale, but it's fine here because we'll use it locally. And then we use caching to remember the results. So when you get back the response to an ARP query, you cache that in your ARP table for a while. The same thing with DHCP. Murphy talked about you have a lease. So you get a response, you get your IP address, you hold it for a time that's a lease period. And then periodically you refresh it. If you don't refresh it, the DHCP server takes it back. Yeah. Mm-hmm. Sorry, repeat the question again. Yeah, so this is DHCP will only actually get broadcast on your local network. So the only value for that IP address is it tells you your stack to convert it to a layer 2 broadcast address, which in this case would be the Ethernet broadcast. But you're never actually, you don't have a router that is looking at the broadcast IP address and saying what's my next hop, and then at the IP layer sending it out over multiple interfaces. You actually rely on L2 to broadcast. Yeah.
Why don't we all use a router IP, and then the router, when we receive information, knows which device is using the network? Wouldn't we take too many IPs? Like we all have the same IP address, which is the router IP, and then if we want to send packet or receive packet, we send to that IP, and then when the router receives it, it forwards it on the local network.
This is your question underlying this, if I'm following where you're going correctly, is this would be a way of doing IP without needing L2. Is that where you were going with that question? That we all send our packets to the router and the router knows where all the hosts are, so why did we need L2? So, think about it this way. What if you were multiple hops away from that router? Right? How would you know? You might know the IP address of that router, but how would you know to get there? You would have had to bring up your IP level routing protocol before anything else can work. But you're right that you could do it. I think if we added flooding to an IP network, some kind of scoped flooding, and we had this kind of strict ordering where you said, I am going to bring up internal routing before I can do things like DHCP or connect host to my first hop router, then yes, we would have had the equivalent of what L2 does. But it's a mechanism that IP doesn't have and doesn't need when you have Ethernet. Where was I? Okay, I was here. Caching. What happens if your client, you get a DHCP address and then you go down? What happens to your address? I just want to hammer home the value of this kind of lease, this notion of a time to live or a lease. So I got an IP address, it has a lease, and then I crash forever. There's no problem, right? The DHCP server, after the lease expires, it's not hearing a refresh request. So it reclaims the IP address. So we've not lost any IP addresses. What if the DHCP server crashed? Yeah. Right, so typically you would refresh your lease, but if the DHCP server is down, at some point in time, you won't get a refresh, so you would you would not have an IP address anymore. So you could even just bring up a DHCP server from a cold start, and everything restarts itself just fine. You would have some outage time, but the system would bring itself back to a correct state. People avoid having the outage time by having multiple DHCP servers, but even if you didn't, the system would come back to a correct state. That's the nice thing about this, what we call soft state, that I have state for a certain amount of time and then I refresh it. And if I can't refresh it, then I just delete it. Bootstrap and discovery. So we said a host is born with only its MAC address, and it had to discover additional information. So we should now know, let's say this is a host A, right? Where does host A get its IP address? We should now know that's DHCP. Where does host A get B's IP address? So A wants to talk to B. We did that too, but it was not a Bootstrap protocol. DNS, right? You have some name, you resolved it into B's IP address. What is B's MAC address if B is local? We used ARP, right? What is your first hop's router's IP address? How did we get that? It's too much of a protocol soup. DHCP, right? So DHCP gives me my IP address, my net mask, which is my prefix, my first hop router's IP address, and my DNS resolver's IP address. All of them IP addresses, because DHCP is bootstrapping L3, but it's bootstrapping IP. So it's giving me IP addresses for all of these. DHCP tries quite hard to be agnostic to L2. Okay. What is my first hop router's MAC address? Where did I get that? Oh. Okay. Any questions here? The examples with the walkthrough we do is not going to make sense if these answers don't make sense.
Like when a host has like cable to pack, does it know the IP addresses of its neighbors?
You're thinking of like a router with two links, with a link connecting it to another router, or you?
Anything, like at home, I have like maybe a
Right.
router and maybe like another router and like somewhere there, like it's like a simple topology, but still
Right.
has some connection. So, and I know my first hop router's IP address. How do I like?
Right. Okay, great. So you are a host, right? You have your host. It has one interface connecting it. The only thing that host knows initially is its MAC address, right? That is burnt into that interface. So what's the first thing the host is going to do? It's going to come up and it's going to say, I need IP level information. It's going to broadcast a DHCP request saying, give me an IP address. It's going to get back a response that gives it an IP address, the IP address of its first hop router, and then other stuff that we'll ignore for now. Okay. So I have those two IP addresses. Now if I want to get out of my network, right, so somehow I have an IP address of some destination. Let's not worry now about where you got it. And so I want to send a packet. Right. So I take that packet and I say it's not in my network. What is it that tells me whether it's on my network or not? The subnet, the mask. Okay, so I look at my own IP address, which I now have. I look at the IP address of the destination and I compare it to my mask. And I say this host is not on my network. That tells me I need to go to my router, my first hop router, because my router is going to get me out. But I only know the IP address of my first hop router. So what am I going to do? I'm going to ARP, saying, I'm going to broadcast again on my local network saying, what is the MAC address of my first hop router? And so my first hop router is going to respond saying, this is my MAC address. So at this point, I have all the information I need to get the packet to that router. I'm going to create a IP packet to the destination, put the MAC address of the first hop router, and send it over Ethernet. And the Ethernet or L2 network is going to carry it to the first hop router. And then the first hop router is going to take it from there. Yeah. And we'll step through that in a minute. Yeah. You want the router to broadcast the... let's not go into malicious routers. Just if you want it to be a malicious router, there's just so much you could do that just drop packets is probably the easiest. Was your question limited to malicious routers or? Okay, so let me maybe jump between the examples and. Actually, let's keep going through this. If it's not clear, the step-by-step operation, when we get to the examples, roll me back. Okay, so more questions. What's the difference between broadcast and flood? We've talked about flooding when we did spanning tree and so on. Not quite. So the difference is actually that broadcast is a communication abstraction that says, I want this packet delivered to everyone. Flooding is actually a mechanism that forwards the packet to everyone. But it doesn't necessarily mean, you can use flooding to implement broadcast. It's a natural way of implementing broadcast. But sometimes, if you remember from learning switches and so on, when you didn't know where the destination was, you flooded it. But your goal was not to reach everyone. Your goal was to reach the one destination that you didn't know where it was. Right? So flooding was a technique that we used to get the packet to everyone. Broadcast, the goal is actually to deliver the packet to everyone. So it's a very subtle difference. And typically we use flooding to implement broadcast. So in terms of communication abstractions, at this point we've studied 4 of them. Unicast, Anycast in the context of DNS, when we said you want to get to any one of the root name servers. Remember your DNS lecture? Multicast was when we said we want to get a packet to a group of receivers. We don't talk too much about multicast in this class, so don't worry about it. And broadcast is we want to get the packet to everyone. Okay, that's the goal of the communication abstraction. So you can think of broadcast as a special case of multicast in the sense it's a group with everyone in it. Okay, what packets does a host operating system see? So now let's say we're in a shared Ethernet context, and there are all these packets going around on the cable, on the shared media. What packets is the network interface card actually going to pick up and send up to the host OS? How do you know whether they're supposed to be for that host? The layer 2, the MAC address. Okay. So your network interface card, or L2, listening to a shared Ethernet medium or listening to its cable, looking at all the packets that come in, is going to pick up a packet if the destination MAC address matches the host MAC address, or if the destination MAC address was a broadcast MAC address. Also, if it's a multicast MAC address for a group that the host belongs to, but we're not going into multicast, so don't worry about that. Okay, so this is your network interface card, looking at all the packets going back and forth, flooded, unicast, whatever packets. The ones it picks up are ones destined for itself, which is basically my address or broadcast packet. So if you flooded a packet with a destination MAC address that was not yours, that host should not pick up the packet. Or rather, it'll see the packet on the wire, but it's not going to send it up to the host operating system. What if I sent a packet that had Sarah's MAC address, let's say, but Alex's IP address? What would happen? What would Sarah's operating system see? Not that you have no bad analogy, but. So if you're a host, you receive a packet, it's your MAC address. but it's not your IP address. What would happen to that packet? Okay. So you will, the network interface card will pick up the packet because it has the right MAC address. It will pass it up to your OS where your IP implementation is. There you're going to look at the IP address and say, this was not my packet, and drop it. Okay. Last one of these slightly tricky questions. Is ARP an L2 or an L3 protocol? L2. Yeah. It's a little confusing as an answer. It's an L2 protocol. If you go back and look at Murphy's slides, you have an Ethernet header. There is no IP header on an ARP packet. It's just an Ethernet packet. But it tends to get confusing to people because ARP is translating between an IP address and an L2 MAC address. Right? So the IP address is like a parameter to the protocol. But on the wire, if you look at the packet, it's a Ethernet packet. Right? There's no IP header on an ARP packet. Right? Questions? L2 and L3 have separate forwarding and routing. We know this. At L2, we've done learning switches, STP, flooding, all of that. If you have a shared medium Ethernet, which honestly I don't think there are very many of them left these days, routing is kind of trivial. You just put the packet on the wire and you're done. IP, we've learned about all the ways in which you do IP routing, from having configured routing entries, either static entries or default route entries, or whatever we've learned through routing protocols like OSPF, BGP, and so on. Remember, always a data packet generally contains both an L2 and an L3 header, with L2 and L3 addresses in each. L3 addresses are global. That means they stay the same from the source to the destination. The network doesn't mess with, for the most part, with IP addresses. But the L2 addresses, and we're going to see examples of this, they change as you go from one L2 network to another along the end-to-end path. And so a packet is generally forwarded on this combination of L2 and L3. We'll get to it in a minute. So what about routers? This is something that might have been easy to miss from Murphy's lecture. He had this example up here, and he had a router, and if you notice, this router has two interfaces, and it also has an L2 and an L3 address for each interface. Okay? So on this side, the router is participating in this L2 network, and on this side, the router is the receiver on this L2 network. And it has an IP address for this interface that belongs to this subnet, and an IP address on this interface that belongs to this subnet. Okay? So we have an L2 and an L3 address per router interface. So a router might interconnect two L2 networks. That was this example. There's another one that I want you to think about, which is that you can have two routers interconnected by a quote-unquote Ethernet network. It's really just a single link. But from the way the protocols work, it's effectively a separate Ethernet network. So this is like one Ethernet network that has two hosts on it, or two MAC addresses on it. This is a separate Ethernet network with two MAC addresses on it. Yeah? Yeah, that's the next slide. Hold on to the question for just a minute. Okay? Does this picture make sense to everyone? Yeah? If it's confusing, think about it this way, that the job of a router is to connect multiple L2 or local networks. And so that's why it has multiple interfaces, right? It's connecting to different networks. And each of those interfaces is a participant in the local network that it's connecting to. So more questions. Where do routers get their IP addresses? For this class, we're going to say they're configured. Okay? You could also have something like DHCP. But that's where those interfaces on each router interface got its IP address. We're going to assume the operator configured them. How do routers discover their neighboring routers' L2, L3 addresses? So this is going back to this picture. Like how does R1 discover MAC2A and IP2A? Again, you could manually configure them. That's going to be our assumption. You could be doing ARP. There are also a whole bunch of specialized protocols, something called LLDP, which is link level discovery protocol, and so on. by which a router could discover its neighbor's addresses. We're not going to go into those. So for this class, just say we're going to assume the network operator went in and configured them. Sound good? Okay. So this is starting to get at the question of when are we switching between the two. Let's think about a packet at a host going down the layers. Okay, and this will tell you when you're going between L3 or L2. So you start at the application. It hands some data to L4 with a destination address. L4, this is your transport, just packetizes data and hands a packet with a destination IP address to L3. Okay? What is L3 going to do? It's going to look at that destination IP address and it's going to decide if that destination is on the same network as itself. Are people getting it? So this host is on some local L2 network. So it's going to look at that destination and say, is this on my network? How is it going to do that? By looking at the subnet mask. Okay. If it is on the same network, then your next hop is the destination. And at this point, how are you going to reach that destination? Through L2, because it's on your L2 network. If it's not, then you're going to look at what your next hop router should be. Okay, because that's going to take you closer towards the destination's network. Yep.
When we study the routing code, can you say that, like in this case, the route in this network will kind of advertise routes to like all other frequencies?
Right, that would be from one router to another. We're now talking here about a host and how it gets the packet to, should it send it to the router or should it send it directly over the Ethernet network to the destination? Make sense? Okay. So at the host, it's deciding whether it should send it directly to the destination or the router. And that's based on looking at whether the destination has the same prefix as yourself. If it does, so at that point, you know what your next hop is. It's either the destination or the router. But in either case, you know the IP address of your next hop. So you then hand the packet to L2. L2 is going to ARP for the IP address, for the MAC address, and then send the packet out over L2. Make sense? Okay. So we got the MAC address and we're good to go. Let's now think about traveling up the layers at a router. And this is going to get to where the routing protocols and so on come in. Okay, so now let's say that a packet arrives at the interface for a router. Okay, and it's now at the L2 implementation at that router. Okay, that interface had a MAC address. What is the router going to do? It's going to say if the destination MAC matches the MAC address of this interface, right? What is that telling me? It's telling me that at the L2 layer, this packet was destined for the router. So it's reached its destination at L2. Is this making sense? Yeah? So at this point, you're done routing at L2. So what should you do? You strip off the L2 header and pass it up to L3. Right? And now I look at the destination IP address in my IP level routing table. How did I build that? Through all of the routing protocols we talked about. Okay, so I now have the outgoing interface at the L3 layer. Right. And now how I just send the packet out over that interface using exactly the same steps as from the previous slide for how you send a packet down the layers. Okay. Making sense? Okay. If it's not, so that means the destination MAC address was not the MAC address of this router. That means that you're still traveling through your L2 network. So you're going to look up the destination MAC address and figure out what the next hop is. But you're now making an L2 forwarding decision. Right? What is the case where I got a packet, an Ethernet packet with a destination MAC address that was not my MAC address? It means I'm an Ethernet switch. And so at L2, I have an L2 forwarding table, and I'm forwarding based on that. Okay. So what is this telling us? If you look at the stop level, what's going on here is the packet is crossing from one L2 network to another. Right. It reached the router. You were done with one L2 network. The router passed it up to L3, and then the router passed it down to a different L2 network. This is, inter-networking. This is literally jumping between two L2 networks. This step down here is the packet going across an L2 network. Got it? Let's work through an example. I'm happy to come back to this after we've done the example, and let me know where things are not clear. So let's start putting this all together. Let's say that we have this figure here with, this is Soda Hall. Soda Hall, for whatever reason, is running shared Ethernet. We have a bunch of hosts. I'm using MAC and IP, that notation, just to make it slightly simpler. And we want host A to send a packet to host B. Okay? They're on the same network. So what are the steps? Let me do this one, and then this one's actually, I think, simpler, and then I'll hand it over to you guys. What path does the packet take in this case? Right? It's directly A to B over the shared Ethernet. A just has to put the packet down, B has to pick it up. What are the L2 and L3 addresses in this packet? So think first of the L3 addresses. It's going to be, the destination is the IP address of B, source is the IP address of A. That's always the case, right? It's the source and destinations. And the MAC addresses are just going to be their MAC addresses. Right? If you think about the routing decision in this case, it was made by host A. The way it was done was host A looked at B's IP address, said, my IP address and B's IP address share the same subnet mask. They have the same prefix. And hence B is on my network. So I need to ARP for B's MAC address. And then I got B's MAC address. And then I sent a packet out over Ethernet with B's MAC address and my MAC address. Yep. In this particular example, this is the shared Ethernet example from Murphy's lecture, where this is not switched Ethernet that we studied earlier. So it's actually a shared medium link. Everything that gets put on the link goes everywhere. Any questions here? Okay, so now let's make it a little bit more complicated. Let's say Corey Hall has a switched Ethernet network. Okay, but it's still L2. These are now a bunch of Ethernet switches, S1, S2, S3. It's the same notation that Murphy was using. And S1 is connected to router 1. And so because of that, we now have the router 1 has yet another MAC address and IP address associated with that interface. And now we say that host A wants to send a packet to host C. Okay? So first, what path does the packet say? And let's say, we're going to make up a spanning tree. Let's say that the path is going from A to R1 to S1, S3, and C. Okay, that's our path. So now let's talk about what the packets look like at each step. Can you think about what the L2 and L3 source and destination will look like on a packet when it is arriving at R1? So that means along this link. Let's start with the IP addresses. That's always easier. What's the source IP address? You can just say it out. A. What's the destination IP address? C, right? IP is end-to-end, so you need C's IP address. What is the source MAC address for a packet that's here? A. And what is the destination MAC address? R1, right? Exactly, because we're getting across one L2 network, and we needed the MAC address of R1. How did we get it? We ARPed. How did we get R1's IP address? DHCP. Okay. So that's at that point. What about, based on what address now is R1 making its forwarding decision? So now think back to the layering we talked about. So packet came in at R1. It said this was my MAC address. So I'm going to take off the Ethernet header, pass the IP header up to my routing layer. Inside this router, I'm now going to look at C's IP address. And let's assume that we had statically configured routes at R1 that said this subnet's prefix go this way and this subnet's prefix go up. Okay, so those are the IP prefix table that I'm going to look up at R1. And I'm going to say my next hop interface is going out on this interface for the C's IP address. Are we good with that? I see some smiles and some no's. What can I clarify?
No, I'm just thinking, and this all happens with
Yes.
Like we also have BGP, but that's like on the global.
Yeah, we're getting there. We're getting there. Right. So how did R1, you're worrying about how did R1 get those entries in its IP table? We statically configured them in this case.
For a second, thought that they're like running BGP.
No. So all these switches are just running L2. There's only one router. There's only one IP router in this picture. Okay. So we had an entry that said C's prefix goes out over this interface. Okay. And now what does it do? If you go back to our walking through the layers, it looks at the prefix mask for this interface and the prefix corresponding to IP address C. So you ask yourself the question, is this destination IP within my local network here? The answer is yes, right? So how am I going to reach C? I'm going to reach it by Ethernet switching, by L2 forwarding, for which I need to know C's MAC address, for which R1 is going to ARP for C's MAC address. Once it gets it back, it's going to forward the packet over Ethernet. Okay. So the address that R1 is making the decision based on is the IP address, because it's acting as a router. It's connecting to networks. And if you ask what routing entries does R1 have, I think that was your question here. It has static routes for the prefixes for Soda Hall's subnet and Corey Hall subnet. And now we're assuming they're statically configured. Got it? What are the addresses when the packet arrives at S3? So this is a harder one now. What are the IP addresses? What's the source IP? The IP address is always easy. The IP address is, source IP address is A. Right? Destination IP? C, never changes. Source MAC address? R1, R1B, great. Destination MAC address? C, perfect, cool. Okay, great. Now let's make this a little bit more complicated. So now let's say R1 is connected to a campus router R2. And just for simplicity, I'm further simplifying my notation here. And let's assume R2 is connected to other routers, but R1 isn't. Okay. Continuing a little bit with our configuration, we're going to say, what static routes would we add to R1? Thoughts? I don't want to run a routing protocol just yet. So I'm going to put in a route at R1. So remember, I already had an entry to go up to Soda Hall and another entry to go down to Corey Hall. You need one more entry at R1. Yep. A default route that says any other prefix on the internet, go to R2. Right? What route would we want at R2? What routes would we want to configure? Soda and Corey. So we would say Soda's prefix go this way, Corey's prefix go that way. If they aggregate, even better. You didn't have to. You could have run a routing protocol between R1 and R2. We could have run OSPF, for example. I'm just simplifying it for this example. So now let's get to the overall picture. So now let's say Berkeley connects to a router R3 in AT&T's network. Okay. And maybe also connects to another router in some different network, but let's not worry about that now. So now Berkeley is connected to the rest of the internet. What does this mean is that R2 and R3 are running BGP. So now we're back in that end-to-end world. And then expand it all the way out. Let's say there was another switched L2 network here that also is connecting to AT&T and so on. Is this picture making sense? Okay. And way out here, this is another switched L2 network. And this is actually in practice how networks tend to look. You'll have L2 networks kind of on the edge, and then you'll have the core that is not that much. You won't find switched Ethernets in the middle of AT&T's network. Typically. We have Ethernet if we think of this as one Ethernet network, but otherwise we don't tend to have these large switched Ethernet networks in the core. So scenario 5, last one, and then I will hand off to you. Host A sends a packet to host D. Okay, well, let's look at what are the L2 and L3 addresses in the packet when it arrives at R2. So I'm going to simplify IP addresses. You have A is the source, D is the destination. That is always the case. What about the MAC addresses? What's the source MAC address? Yep. R1C and destination? Out to A, exactly. So we're treating this like its own Ethernet network. So it's kind of like a redundant, highly simplified path through an Ethernet network. It's just going across that link. What about the addresses when the packet arrives at S6? Again, I'm going to tell you the source and IP, destination IP stay the same. What about the MAC addresses? So we're now here. What's the source MAC address? Yep. R20B. Great. And destination? D. Yeah, perfect. Any questions on this? Yeah. You could certainly have multiple routers within, like multiple gateways here, you mean?
Maybe like a set of switches within a router instead.
Over here? You could. This gets back to the question of, in that case, this would not be your L2 network. It would be an IP network. And you could be running something like OSPF or something within this. Yeah. Right. Right. Right.
But so inside one L2 network, that usually have just kind of like one gateway inside have those.
Yeah, so think about it this way. You always have L2 connectivity between any two nodes, right? Because when you put a packet out, there's always an Ethernet header and an IP header. So even if I put a packet here, look at a packet over here, it has an Ethernet header and it has an IP header. So the question is really, are you forwarding at L2 or are you forwarding at L3? Right? I think that's maybe, when I take this switch over here, it's only forwarding based on L2. It never looks at an IP address. Whereas if I look at these routers, they're always looking at the IP address. And then they're also putting the Ethernet source and destination MAC. The L2 forwarding is trivial in this case, but it exists. Your Ethernet header is there on the wire. And that is exactly what confuses people. So that is the rules about when you're forwarding at L2 versus L3. Right? You always, in a router, you always look at L3 and you always pick your L2 addresses as well. So really the question is when you only look at L2, and it's one of these switches in your L2 network. Does that make sense? Sarah, do you want to switch? Yeah.
So when we have these two routers at somewhere in the middle of each other.
Right. So you could have done, that was the question on the routers and how do routers discover their neighbor's IP address and MAC address. We said we're going to assume they're configured. But you could be doing ARP. If I sent an ARP message over here saying what's the MAC address for the IP address on the other end, that interface should send me back a response saying this is my MAC address. Any other questions? Right.
Okay. So I'll go through a couple demos. I'm actually going to skip over Sylvia's next part of the lecture so that you guys can see both. So first we'll talk about these bootstrapping things that we were just discussing. I do want to note that what I'm going to show you is a lot uglier than the pictures that we look at. But this is hopefully to allow you to relate what you can actually see on your own computer to the prettier pictures of things that we've looked at in class. So we're going to see what DHCP and ARP look like on my own computer when I'm connecting to my Wi-Fi at home. Is it going to let me click? Okay, there we go. Yeah, so this is Wireshark, a common tool used for networking things if you haven't used it before. Hopefully this is large enough that you can read it. But the exact details don't really matter here. It's just that this is the homepage of it. You have a bunch of interfaces. You can select them to look at all the packets on that interface, and we'll be doing that in a second. In particular, what we're going to look at is the Wi-Fi interface EN0. So first, let's look at what our Wi-Fi interface is actually doing. So I'm going to use ifconfig in the terminal. So this will give me a bunch of information about that interface. A lot of it is not important here. Again, things are dirtier in the real life. But what's important here is that it's both inactive and we can see its Ethernet address, because regardless of whether it's up or not, you will always know your MAC address since it's burned into the interface. So I can also look at the routing table for my computer. I will note that right now, because this Wi-Fi interface is inactive, I turned off my Wi-Fi, like the way you do in the drop-down menu. So when I show my routing table, it's going to have a lot going on here. That's all IPv6 stuff. Let's ignore it. I have the IPv4 highlighted here. Let's pretend that's the only thing here. And you'll see that all the routes go out on this loopback interface, LO0. This is a purely logical interface. It's not actually a physical thing on my computer. That's why it's still here. It's used a lot for like web development, so you can host something locally at like 127.0.0.0. But that's all that really matters here. Okay, so next we can look at my ARP table as well. And what that will look like is nothing for now. I'm not connected to the internet, so there's nothing in my ARP table, or not connected to anything. Okay. So now let's go back to Wireshark and start collecting packets on my Wi-Fi interface before I start turning it back on. So what will happen is I'll see every single packet that touches this interface going in and out. So if I drop down and turn on my Wi-Fi, then we're going to see all of this. This is a lot of information. We're only going to look at a few select packets here. Again, I just show this to show you that there are other things going on. But yeah, we'll show how to filter this later. But for right now, I want you to kind of see that there will be outputs like this. So first, we can look at this ARP request. And it is asking for who has this 192 address. And if we go back to the interface config for my Wi-Fi interface, we can see the Ethernet address. It ends in this 7E19. And if we go back to this ARP request, we can see that's where it's coming from. Wireshark is resolving sort of the beginning part of that to make it more human readable. So it has Apple 3C and then the last 4 digits there. But yeah, so it just resolves it to make it more human readable. That is my MAC address. Okay, so then in this bottom pane of Wireshark, we can look at specific fields in the headers of the packets that we're looking at. And so here in this ARP request, we can actually look into the ARP fields and see what's going on there. Some unsurprising things are that the sender MAC address is that MAC address that I just talked about, and the target one is unknown, so we just fill it with a bunch of zeros. But there are 2 things shown on this screen right now in the bottom pane that are not quite what we would expect. Does anyone know what they are? Okay, I'll give you one. For one, if you look at the Ethernet header right above this ARP header that I have highlighted, there is a destination address. This surprised me too. I think this goes into limitations of my Wi-Fi knowledge. I think because I have connected to this Wi-Fi before and have gone through like the authentication process, it does know the MAC address of my router. Another surprising thing is in the ARP header. Any guesses? Okay, I have a sender IP address, but I have not done any DHCP yet. Again, this is my home Wi-Fi. I connect to it a lot. So I already had a lease for this IP address, even though I wasn't connected right before we started this. We'll see in a moment that there is, in fact, DHCP. I make sure I'm still allowed to have this IP address, but I, for right now, assume I have it. Okay, so now if we move on. Oh, that was just to look through all of that. Okay. Yeah, so now we can look at the I should go back. Sorry. We can look at the DHCP request. And so since my computer already had a lease for this, it asks for that specific IP address that it already had. We can look at the specific internals of this request. A lot of it is not that interesting. There's just a lot of information. But the more we scroll down, we can see my MAC address, we can see the IP that I'm requesting. We can also see that I'm requesting a lease time of 90 days. We will learn that I will not get that. Yeah. Okay, so then next in the list of packets that we're going to look at that are interesting is our ARP response. So my router replied and said, I have this IP address. So that's all set up now. I know that mapping. And we can also look at the DHCP response. Again, lots of fields, but we can scroll down and see that I did, in fact, get the IP address that I wanted. I only got a lease of 8 hours, and the domain, it also gave me my DNS server. So that's critical information for the future, because if you look down a little bit, I do then send some DNS requests. This is just some stuff that my computer was doing for whatever reason. It's not caused by any request I started, but we can also look inside the DNS request as well as the response. Okay, so now let's go back to terminal and look at what changed. So if I look at my interface, we already looked at my interface. If we look at my ARP table, now there's a bunch of entries. In particular, there are other MAC addresses on my subnet. That is my home network. And then we can also check the route table again. Again, we're going to get a lot of IPv6 output. Let's ignore that. Let's go back up to IPv4. The table has gotten bigger. You'll notice a lot of the outgoing interfaces are now my Wi-Fi interface. The most important thing here is that first route. I have a default route through my router as my gateway, and it goes out on my Wi-Fi interface. Okay, any questions on any of this? Yeah?
I thought the DNS is pre-configured when you're hosts file or something.
So you can, I think if you go into your network settings, you can specify a particular DNS server. I think that would be a rather special case thing. In general, DHCP tells you where to go for DNS resolvers. Mm-hmm. Why was there an ARP request? Yeah, I think this is another artifact of the fact that I have connected to this network several times. So as we saw, I knew both what I expected my IP address to be and what I expected the gateway IP to be. And so I think it was resolving that IP. But yeah, again, this is just showing that if you test this out in your own home network, you're going to see things that don't quite match our perfect view of starting from zero state, as there is some pre-existing state, especially in your home PC. Yeah. I don't know if I'll make a blanket statement, but it seems like in Mac implementations, they try to keep their consistent IP if they can. But yeah. Okay, cool. Then I will move on to the second demo, just so that we can make sure we get it in. So a little bit of a topic change. Now we're going to get into web things. Again, I want to show how to make this look real. So first I'm going to take a look at this just through the lens of HTTP. We're going to ignore packet level things for right now. So I have this example website that I made. It is just a very small HTML file with an image in it. That is all that's going on. So I'll begin by opening the Inspector tab on Chrome. If you're not familiar with this, it's really useful, again, for web development. So, for example, I can look at the HTML, and as I hover over it, it will show me what that actually looks like in the web page. But what we care about is the Network tab. So I'll go over there. and we can see what the browser is using the network to do with this. At first, it's empty because it doesn't record unless it has to. And this will give us a lens into how the page is loaded at the HTTP level. Keep in mind, these are not packets. So I'll reload the page. And so you can see that we sent 2 requests, one for the website overall and then one for the image resource within it. So then we can look specifically at what's going on within these requests. So you can see the headers. In particular, we can see that this was a GET request, that we got a status 304. So what does this mean? Does anyone know? Yes. Right. So I have obviously loaded this page before, so it hasn't changed since I last got it. So I got a 304. And then there's a whole long list of HTTP information that you can look through if you care about, but it's all there. And then we can look at the preview. It's the HTML file without the image inside it. And then the last interesting tab that we'll look at here is the timing tab, where you can see how long it took for different phases of the request. So here, the content download dominated in all of the different ways you could spend time. Okay, so now we can look at the image request. Same thing. If we look at this headers tab, we can see that we got a 200 response, and actually it was from the memory cache. So since I had loaded this page before, Chrome cached the image for me so that when I reloaded it, it just loaded it locally. Again, we can look at all the headers. The only notable thing here is that when we get to the bottom, we'll see the request headers are provisional. This is essentially just pretending what it would have been if we actually had sent a request, but because it was stored locally, we didn't. And then, again, we can see a preview of the file. And if we go to the timing tab, we can see that we spent essentially no time downloading the content since it was stored locally. So we can disable the cache at the top of this Inspect tab, and then we can reload the page and see what happens. So now we have 200s for both requests. We're only going to look at the image one. But now you can see it wasn't allowed to use the locally cached version, so it no longer says it came from the memory cache, and it actually grabbed it from the server, which, yeah. So now let's see what happens if we load a much more complex website. So google.com, there's all these assets, a bunch of HTTP requests, all doing a bunch of different things. So you can play around with this on your own time on any website there is, but yeah, our initial one was just for cleanliness. Okay, so now let's take a look at the exact same thing, but at the packet level. So again, I'm going to bring up Wireshark. I want to note I'm no longer on my home Wi-Fi here. I'm now in Soda Hall, so I have 2 active interfaces. I have my Wi-Fi interface and a wired Ethernet interface. So that's EN0 and then the Thunderbolt EN6. So let's first see what's going on my Wi-Fi interface. And the answer is a lot. You'll see those black TCP ones. Those are retransmits, so this just demonstrates to you that this happens a lot. You're going to see a bunch of protocols. They're also color-coded. So QUIC is a protocol we haven't actually talked about, but it's built on UDP. There's a lot of TCP going on. And yeah, I could scroll like this forever, but the point being that this is pretty hard to read. So we're going to do some filtering to make this easier to look at, so that if I load this page on the right, I can actually find what's happening. So we can close that out, and then we'll look at the Inspect tab on the right, and we'll get some information that we can filter on in order to not be overwhelmed. In particular, this remote address in the top, as well as the port, will be good things for us to filter on. We can only grab packets with those fields. And so Wireshark lets you set up filters. We don't have to get into the exact semantics or syntax of it. But I'll just insert this this filter so that we get everything on TCP port 443 and at this IP address. So now, if I listen on my Wi-Fi interface again, and I reload the page, there's nothing. Any ideas why? good guess, but no, I actually still had the caching turned off. Yeah. So the reason is a little bit tricky. I knew when I created this filter that filtering on an IP address was probably a bad idea because I'm using GitHub hosting. I don't know how they do it. They can move it around servers arbitrarily. So if we look at the IP address of the new request, it actually slightly changed the IP address. So now I'm just going to edit the filter to that slight change, and now we can see everything that's within this request. So taking a closer look, we can again see all the packet header information in the bottom pane. There's a lot going on here, but you can drop down based on which protocol it is. And in particular, there's all this TCP information inside of it. And in particular, we can see if we look at the top that the connection does in fact start with a SYN, SYNAC, ACK, as we've always talked about. And yeah, so that's one of the clean parts that actually did make it through here. And then we can look at what goes on after that. We get some application data. There's also some additional connection setup at the TLS level, so the two ends decide on a cipher. We don't have to care about that too much in this class, but just to help you understand what's going on. And then we can also look at the application data. But since we are using TLS, it's not very exciting. It looks like nonsense. I can open the TLS part of the packet, and there's just nothing to look at in Wireshark. It's not going to be readable in any way. So I can close this out. And then we can try to do this on a website with no TLS. So we will hop over to Sylvia's very old website. To her credit, she didn't even know the department was still hosting this. So if I then filter on the IP and port from the Inspect tab for this website and then open up my Wi-Fi interface and load the page, I again get no traffic. Any ideas on why this is? This is a bit tricky. Yeah? 443 is for HTTPS. So it's port 80 for HTTP. Okay, so this is a bit nuanced. But if I close this session out and I try it on my wired Ethernet, it will, if we retry, it'll work. So I gave you what fixed it. Do you guys know why? Yeah? Exactly. Yeah? Oh, so all of this is recorded. But, yeah. Because the Wi-Fi in here is flaky enough, I wasn't going to trust it. So, yes, this is exactly it. I mentioned at the beginning very briefly that my wired connection is in SOTA. It makes sense that this website at eeks.berkeley.edu is also hosted probably in the same building, definitely in the same subnet. And so when the packets with a destination IP for this IP showed up on the interface, the route that was chosen, longest prefix match, was on the interface that's also on that same subnet. So, yeah, now we can look at application data, looking more specifically at this. You can see, for instance, there's that GET, and we can actually look inside it as well, since there's no TLS. And yeah, you can see all the HTTP information we saw in Chrome originally. So, one thing I do want to note before we move on, there's no SYNAC handshake at the top. Any guesses for why? Yeah? Yeah, so browsers typically will keep your TCP connection going for 60-ish seconds. And so when I loaded the page the first time and it didn't work, that initiated a connection. There was probably a handshake then. But then when I reloaded it, it was in a short enough amount of time that Chrome just used the connection it had to the server. Okay, So now we can look into all the application data we want to. You can see the response header, look inside of that. Most of it is pretty human readable. It gets pretty ugly when it's at the byte level, but it's all there. And then I also want to note that just in these boring TCP packets with just some random application data in them, you can see a bunch of interesting information like the advertised window size, what the sequence and ACK numbers are. Wireshark also gives it in relative form so that you can reason about it a bit more easily. And then we also can see things like we get a separate request for the actual image. This follows what we talked about at the HTTP level. And we can scroll all the way down through all these packets to see some FIN packets and the eventual termination of all the connections that were a part of these HTTP requests. Okay, any questions? Yeah, so you can Google Wireshark, download it, play with this yourself, see what does and does not match your understanding of things, and yeah. Okay. I gave Sylvia a very small amount of time. Okay. Oh, okay.